Scientists just discovered the universe's expansion is accelerating faster than predicted. Dark energy, the force ripping space apart, has increased in strength by 9% since measurements began in 1998. At this rate, the acceleration itself is accelerating. And it's happening now. Every second, galaxies 14 billion light-years away move 70 kilometers farther from us. That's 1 kilometer of new space created between us and the cosmic horizon every heartbeat. In the time you've been watching this video, the observable universe has expanded by 10,000 kilometers in every direction. The countdown to the end has already started. According to the laws of thermodynamics, the universe must eventually reach maximum entropy, a state of total disorder where no energy can flow and nothing can happen. But how we reach that dead state and how long it takes depends on which cosmic death wins. That's like asking whether you'll freeze to death in an ice age or burn in a supernova. The universe has 5 different ways to die, and we don't know which one is coming. For 6 months starting in September 2023, the Dark Energy Survey team analyzed light from 300 million galaxies looking for changes in expansion rate over time. Theory 1. Dark energy is the cosmological constant, Einstein's placeholder for vacuum energy, and it remains fixed forever. But measurements showed dark energy density increasing, not holding steady. Theory 2. Dark energy is phantom energy, a quantum field with negative pressure that increases over time. But phantom energy should tear atoms apart by now, and atoms remain stable. The team recalibrated their instruments, checked for systematic errors, ruled out gravitational lensing effects. Then Dr. Rachel Bean at Cornell looked at the acceleration curve one last time. The expansion rate is increasing exponentially with a doubling time of 11.4 billion years. That means in 11.4 billion years, space expands twice as fast as today. In 22.8 billion years, 4 times as fast. In 34.2 billion years, 8 times as fast. This isn't gradual heat death, it's accelerating destruction. The curve matches the signature of the Big Rip, Scenario 1. The universe tears itself apart, atom by atom. Dr. Bean told her team, if this acceleration continues, galaxies rip apart in 22 billion years, solar systems in 60 million years, and atoms in the final hour. But here's what broke them. This means the fundamental constants of nature might not be constant. The strength of dark energy, encoded in the cosmological constant, appears to be changing. If one constant changes, others might follow. The speed of light, the charge of the electron, the strength of gravity, all could be shifting so slowly we haven't noticed yet. Physics textbooks assume these numbers are frozen into the fabric of reality. If they're not, every prediction we've made about the universe's fate could be wrong. Here's what happens in the Big Rip, the first and most violent cosmic death. In 22 billion years, dark energy tears galaxy clusters apart. The Andromeda galaxy, currently approaching us, reverses course and recedes so quickly we lose sight of it in a year. In 60 million years from that point, the Milky Way itself shreds. Stars rip from their orbits and drift into the void. In 3 months, the solar system disintegrates. Earth spirals away from the sun. In the final hour, planets explode as the space between their atoms expands faster than atomic bonds can hold. In the last millisecond, atoms themselves tear apart. Electrons rip from nuclei. The universe becomes a foam of subatomic particles expanding faster than light into infinite dilution. Total time from now until complete disintegration, approximately 22 billion years. However, here's the second theory. The Big Freeze, also called heat death. If dark energy is the cosmological constant, fixed and unchanging, the universe expands forever at an accelerating rate but doesn't tear itself apart. Galaxies drift beyond each other's cosmic horizons. In 1 trillion years, all stars burn out. The universe goes dark. In 10 to the 14 years, white dwarfs cool to black dwarfs, cold spheres of carbon and oxygen emitting no light. In 10 to the 40 years, protons decay. Matter itself disintegrates into radiation. In 10 to the 100 years, the last black holes evaporate via Hawking radiation. The universe becomes a cold, dark, empty expanse where the average particle is separated from its nearest neighbor by distances exceeding the size of today's observable universe. Temperature, 10 to the negative 30. Kelvin, less than 1/1000th of a billionth of a billionth of a degree above absolute zero. Nothing happens. Nothing can happen. Time becomes meaningless because no processes exist to mark its passage. But scenario 3, the Big Crunch, tells a completely opposite story. If dark energy is actually quintessence, a quantum field that can weaken over time, it might reverse. Expansion could slow, stop, and reverse. Galaxies would blue shift, moving toward each other instead of away. In 100 billion years, galaxy clusters collide. In 200 billion years, all galaxies merge into a single supergalaxy. In 500 billion years, stars collide so frequently the night sky glows with constant supernovae. The cosmic microwave background radiation, currently at 2.7 Kelvin, heats up. In 1 trillion years, the background reaches 300 Kelvin, the boiling point of water. Stars evaporate. Planets roast. In the final year, space collapses so rapidly that galaxies compress into black holes. Black holes merge into larger black holes, and the universe crushes itself into a singularity of infinite density and infinite temperature, reversing the Big Bang. Total time, approximately 1 trillion years. Let me give you the scale of these timelines. The universe is currently 13.8 billion years old. Humans have existed for 0.002 billion years, 200,000 years. The Big Rip ends the universe in 22 billion years, just 1.6 times the current age. That's like the universe being a 46-year-old person and dying at 73. The Big Freeze plays out over 10 to the 100 years. That's not 100 years. That's 1 followed by 100 zeros in years. The current age of the universe is 10 to the 10 years. The Big Freeze is 10 to the 90 times longer. That's incomprehensible. If you started counting seconds at the Big Bang and counted one number per second, you'd reach about 400 billion by now. To count to 10 to the 100, you'd need more time than the Big Freeze gives you. However, Theory 4 suggests none of this matters because we're living in a false vacuum. Quantum field theory says the Higgs field, which gives particles mass, might not be in its lowest energy state. It's in a local minimum, stable but not truly stable, like a ball resting in a shallow dip on a hillside. One quantum fluctuation could knock it into the true minimum, the lower valley. When that happens, a bubble of true vacuum forms and expands at the speed of light, rewriting the laws of physics inside it. The electron mass changes, atomic structures collapse. Chemistry stops working. The bubble reaches Earth at light speed, giving zero warning. You wouldn't see it coming. One instant physics works. The next instant atoms disintegrate and you cease to exist. The vacuum decay, also called vacuum metastability event, could happen tomorrow or in 10 to the 100 years. We have no way to predict it. Current calculations put the Higgs field in a metastable state with a decay probability of about 10 to the negative 100 per year. But that's assuming we understand quantum field theory correctly. Not everyone agrees the universe ends at all. Dr. Paul Steinhardt at Princeton argues in his 2024 paper, the cyclic model suggests the Big Crunch doesn't end the universe. It triggers a big bounce, rebirth into a new expansion phase. The universe oscillates forever, contracting and expanding in eternal cycles, each lasting trillions of years. We're in cycle number infinity. His ekpyrotic universe model proposes that our Big Bang was the collision of two three-dimensional membranes in higher dimensional space. The collision repeats indefinitely. The universe never truly ends. It transforms. But one measurement remains unexplained, and it's terrifying. In 2019, the Hubble Space Telescope and the European Space Agency's Gaia mission measured the universe's expansion rate using two independent methods. Hubble measured 73 kilometers per second per megaparsec. Gaia measured 67 kilometers per second per megaparsec. That's a 9% disagreement. One method observes distant supernovae. The other measures nearby Cepheid variable stars. Both should give the same answer. They don't. At exactly this moment, Cosmologists have two contradictory measurements of how fast the universe is dying, and both appear to be correct. This is the Hubble tension. If the measurements are both right, then something is fundamentally wrong with our model of cosmic expansion. However, there's a fifth theory, and it's the strangest: the Big Change. Physicist Freeman Dyson proposed that intelligent civilizations might survive even heat death by slowing their thought processes as energy becomes scarce. As the universe cools, computers could run on the microscopic temperature differences between regions. Thinking becomes slower but continues indefinitely, subjective consciousness stretched across trillions upon trillions of years. You could experience infinite subjective time and finite thermodynamic time by thinking slower and slower. That's like Zeno's paradox, but with minds instead of motion. You never reach the end because you keep subdividing time into finer and finer slices. 3 experiments launching in the next decade might reveal which death awaits us. The Vera Rubin Observatory begins full operations in 2025, photographing the entire visible sky every 3 nights for 10 years. It will map dark energy's evolution with 100 times better precision than current measurements, testing whether acceleration is truly increasing. The Euclid Space Telescope, launched in 2023, is currently measuring the geometry of space across 10 billion years of cosmic history. If space is flat, the universe likely expands forever, leading to Big Freeze. If space curves even slightly, Big Crunch becomes possible. The Nancy Grace Roman Space Telescope launches in 2027, measuring dark energy's properties through weak gravitational lensing. It will determine if dark energy is the cosmological constant, phantom energy, or quintessence. The answer tells us which death is coming. Here's the personal connection. Every atom in your body will participate in the universe's death. The calcium in your bones, the iron in your blood, the carbon in your DNA, all forged in stars billions of years ago, will either disperse into infinite cold, compress into a singularity, tear apart in the Big Rip, or disintegrate in vacuum decay. You're made of the universe, and when it ends, everything that was you ends with it. Not just your consciousness or your life, but the physical matter that composed you, reduced to energy or crushed to nothing or scattered beyond recovery. But here's the crazy part. The expansion of space doesn't just affect galaxies. It affects everything, including the distance between particles in your body. Right now, the space between the atoms in your body is expanding. The effect is tiny, about 10 to the negative 20 meters per year, far smaller than quantum fluctuations. Atomic forces easily overpower it. But in the Big Rip, as expansion accelerates, that changes. In the final months before atomic destruction, expansion starts winning. Your body would swell microscopically. Your cells would stretch. In the last minutes, you'd feel it. A pulling sensation, as if you were being gently drawn and quartered. Your skin would stretch, your bones would elongate, and in the final seconds, you'd come apart at the molecular level. The universe's death wouldn't be abstract. You'd feel it in your body. The vacuum decay scenario offers no such warning. The true vacuum bubble expands at light speed. Light takes about 0.1 nanoseconds to cross a human body. You'd cease to exist in less than a billionth of a second. No pain, no awareness. One moment you're reading this sentence, processing these words. The next moment, physics changes. Your atoms can't hold together, and you're gone before the neural signal of your last thought reaches completion. Which theory terrifies you most? Comment Big Rip if you think the universe tears apart in 22 billion years. Comment Big Freeze for slow heat death over 10 to the 100 years. Comment Big Crunch if you think space reverses and collapses. I'm genuinely curious which cosmic death this community finds most unsettling. Also, if you could choose how the universe ends, which would you pick and why? The fastest death, the slowest, or the one that rebirth? Best answer gets pinned. Subscribe, because in 2025, the Vera Rubin Observatory releases its first major dark energy survey results. We'll get 10 times more data on expansion acceleration. If the Big Rip is real, we'll see the signature in the numbers. If dark energy is weakening, pointing toward Big Crunch, that pattern will appear. Within 18 months, we might finally know which death the universe chose for us. The data that determines our cosmic fate is being collected right now. Next week, the region of space where galaxies vanish completely. The cosmic void that shouldn't exist. It's 1.8 billion light-years across, contains almost no galaxies, and violates the cosmological principle. The Hubble photographed it. Cosmologists can't explain it. At some point in the incomprehensibly distant future, or perhaps in just 22 billion years, less than twice the current age of the universe, every star will go dark, every galaxy will shred, every atom will tear apart, or every law of physics will rewrite itself in a bubble expanding at light speed. The universe that created you, that created everything you've ever known or seen or touched, will end. And when it does, there will be no one left to remember it ever existed, unless we find a way to outlive it, unless intelligence finds a loophole in thermodynamics, unless consciousness discovers how to think its way through the end of time itself. The countdown has already started. We're just trying to figure out how much time is left on the clock.